everyone, I'm Carolyn Heim with the Tsolum River Restoration Society, and I'm down on the Tsolum River with Andrea Travail, the chemistry teacher, and we're interested in looking at the copper levels in the water. The reason we're interested in copper in the Tsolum is because it has a history of a mine that was built near Mount Washington in the mid-60s. And the mine only operated for 3 years, and it wasn't turning a good profit, so it was abandoned. And in abandoning the mine, they left a whole bunch of crushed and exposed rock, which, when exposed to the air and to the rain, formed a chemical reaction. And the leachate from the mine, called acid mine drainage, made its way into the Tsolum, and it decimated the fish populations for about 40 years. So this, the local community became aware of this problem in the mid-80s, and it wasn't until 2010 that a final solution to the problem was come up with, and the whole mine was capped. So our society measures the water every 2 weeks to make sure that the copper levels are below the level that is not toxic to fish.
Right, I'm holding a piece of waste rock from the old copper mine. Now, copper ores are often rich in iron pyrite, and if we look closely at this rock, we'll see that there's lots of iron pyrite in it. It's the stuff that looks like gold, and its common name is fool's gold. Now, the chemical name for iron pyrite is iron 2 disulfide, and that stuff is best left locked up deep underground where it can't cause any problems. Because when iron 2 disulfide is exposed by mining, it is readily oxidized in the presence of oxygen, water and bacteria, and this results in the formation of sulfuric acid. Now, sulfuric acid then reacts with the surrounding rocks, and that causes the release of other metal ions into the runoff, including copper 2 ions. Now, copper 2 ions are not all bad. Indeed, they're actually an essential trace nutrient for humans and for fish. For example, they act as cofactors for a number of enzymes, so they're involved in lots of cellular processes. But at even very, very, very low concentrations in rivers, copper 2 ions cause adverse effects to fish. They cause damage to a number of organs and systems, such as their gills, their kidneys, liver, their immune system, their nervous system, and they even impair their sense of smell. BC water quality guidelines show that the concentration that copper 2 ions are toxic to aquatic life depends on other water parameters. Copper 2 ions are less toxic in hard water when there is a lot of dissolved organic carbon in the water. Copper 2 ions are much more toxic in acid conditions, and hence the devastating effect of the acid mine drainage on the Tsolum River fish population. Now, the Tsolum River Restoration Society has got a low-range copper testing kit, and this is designed to detect copper 2 ion concentrations of 0.05 to 0.5 parts per million, which is the same as 50 to 500 parts per billion. Now, the way it works is you add 5 drops of sodium diethyl dithiocarbamate to a 10 ml sample of your river water. Now, the diethyl dithiocarbamate ions form a golden brown complex with any copper 2 ions that are present, and then you just compare the intensity of that golden brown colour with these standards. Now, the Tsolum River Restoration Society has been monitoring the copper 2 ion concentration in the river to ensure that it is lower than 7 parts per billion. So, as the lowest concentration that this kit detects is 50 parts per billion, I'm not expecting a positive result. Right, so I'm going to add 5 drops of sodium diethyl dithiocarbamate to a 10 ml sample from the Tsolum River. Right, now if there was a measurable level of copper 2 ions present, we'd start to see a golden brown colour forming, and I can't see that. I'll give it a shake, and I still can't see the evidence of a golden brown colour. but this little viewer makes that easier to see. So yeah. Okay, so when I match this up, it's saying that it's 0. So this kit cannot measure the low concentrations of copper-2 ions in the Tsolum River. So the Tsolum River Restoration Society send their water samples to a lab where they use an inductively coupled plasma mass spectrometer to measure the copper-2 ion concentration. Okay, so earlier today I tested a sample from the Tsolum River for the presence of copper-2 ions using a chemical that's new to me, sodium diethyl dithiocarbamate. Okay, now this forms a golden brown complex at incredibly low concentrations of copper. Anyway, we got a negative result. Now, in chemistry, we don't normally talk about parts per billion in our lessons. We talk about concentrations in terms of moles per litre. I just wanted to show you what a 1 mole per litre solution of copper-2 ions looks like. This is 1 mole per litre of copper-2 sulfate. And in terms of parts per billion, okay, this is 63,500,000 parts per billion copper-2 ions. Right, so when we've got copper-2 sulfate, that contains the hexaaqua copper-2 ion, which is blue, okay? And so you can see this is a paler blue, there's vaguely a bit of blue to that, and then we can't really see the blue anymore because they're so dilute, okay? Now, when this forms the complex, okay, this is what it does. So 2 of these ions complex with the copper and form this golden brown complex, okay? The equation is just there, so there's a hexaaqua copper. Along come 2 of these, boot out the water ligands, and we're ended up with this golden brown uncharged complex. This is called ligand exchange, and I thought I'd show you this with a couple of other chemicals which also make different coloured complexes with copper-2 ions. So I'm going to add concentrated hydrochloric acid, which is a concentrated source of chloride ions. That will form the yellow tetrachloro complex with copper. And I'm also going to add ammonia, which will form this dark blue tetraamino complex with copper. Okay, now these are only going to be visible at relatively high concentrations, not the low concentrations that this one is going to be visible at. I'll start first of all with the concentrated hydrochloric acid at 5,000 parts per million. I drop it in. You should see that it's going yellow. I'm adding quite a lot, and it looks a little bit green because there's still some of the hexaaqua complex in there as well, but now I've got it a fairly decent yellow colour. Okay, I'm going to do the same with concentrated ammonia. So this one, first of all, because ammonia is a base, we're getting a bit of deprotonation, so we're getting copper-2 hydroxide forming. But if I add a bit more, I can get rid of that. I give it a little shake. Okay, I've now got the dark blue tetraamino complex. Okay, all right. Now I'll show you what happens when you add the sodium diethyl dithiocarbamate. So just 1 drop. As it goes in, you can see we're getting a brown precipitate. Okay. Now, the reason it's a brown precipitate, just 1 more drop. There we go. The reason it's a brown precipitate is because the complex is uncharged. Okay, so it is But interestingly, when the copper-2 concentration gets lower, the complex does dissolve and we get this golden brown colour. Right, let's now go down to 500 parts per million. So we'll add some of the concentrated hydrochloric acid and we should be getting a yellow colour, but only very just. Okay, will we get a blue colour? Just. And then if I add some of this, in it goes straight away. We're getting that brown precipitate again. Okay, starting to see some of it is definitely dissolving, so we're getting the golden brown happening. All right, now let's move on to 50 parts per million. So add the concentrated. And can we see any yellow forming at all? I don't think so. Let's try with the concentrated ammonia. Are we getting any blue at all? I don't think so. But if I add this, look, golden brown again. All right, lovely golden brown. And we keep on getting that golden brown as we keep on going down the concentration. So there's 5. Here's 0.5. It's still, we need a little bit more in there. But yeah, we've still got a vaguely yellow, and 0.05. Should still see detectable slightly yellow in there. Okay, so this is a pretty incredible chemical. Happily, the copper-2 ion concentration of Tsolum River means that we can't use it to test for it, which is good news. But very interesting for me that it can detect copper at such low concentrations. Okay, so now I'm going to show you a technique that I'm more familiar with for measuring the copper-2 ion concentration of a solution. It is an iodometric titration. So what you do is you add some potassium iodide to your copper-2 ion solution and iodine is produced. You can then titrate that iodine against sodium thiosulfate. Right, I particularly love this reaction because when you look at the reduction potentials of the two half equations, you'll see that this reaction shouldn't be spontaneous. You'll see that we reverse this half equation. So when we calculate E cell, it's 0.15 minus 0.54, giving us an E cell of minus 0.39. So negative E cell means the reaction shouldn't be spontaneous. But you're actually about to watch that happen. You'll see that it is spontaneous. It's going to happen in front of your eyes. So I will pipette out some of my copper-2 solution. So don't know the concentration, that's what I want to find out. So you can see it's a nice pale blue, that's the hexaaqua complex. This is a 25 ml pipette, it's taking a little while to fill. And it's also going to take a little while to empty. Okay. Right, so now I'm going to add excess potassium iodide and you're going to see this reaction happen that according to E cell shouldn't, okay, it shouldn't be spontaneous. But as I pour it in, you will see that a reaction certainly happens. Yep, you can see it's gone brown. Okay, and it's a cloudy brown. Okay, definitely can't see through that. So the brownness is the iodine that's produced, and the cloudiness is the precipitate of copper-1 iodide. Now the fact that we're getting a solid being produced should give you a clue as to why this reaction happens when E cell is negative. Okay, so let's titrate this. So let's read the burette. The burette is at 0.25. Okay, so let's go. So as I add the sodium thiosulfate, it will react with the iodine, turning it into iodide. And the solution should appear less brown. Okay, so now as I drop it, you may see the white colour. The white colour is copper 1 iodide that we can actually see. Okay, so when I remove the iodine from that little bit where I'm dropping it in, we can see the colour of the copper 1 iodide, which is white. Right, now with this titration, starch is really important because, as you can see, it's very mucky and it's quite hard to know when the end point is. Okay, so it's really hard to even to know when we're near the end point. So I'm going to add some starch now, and you can see I'm getting the blue-black colour, okay, and even this is not super clear. Let's put a bit more in. Even more. I don't think I've got a very concentrated starch solution today. All right, so we're looking to lose this blue colour as our end point. Okay, so as I drop it in, you can see that we're getting the whiteness. And now, looks like we are losing that blue-black colour. In fact, pretty much lost it. Just going to get it dropping now. Yeah, and now I can't see any blue-black there anymore. So that is our end. Okay, so that's just the copper 1 iodide. No iodine left, and hence no blue-black complex. Right, so I'll read the burette. That's now at